Hello and welcome to our Wednesday webinar from the International Centre for Sustainable Carbon. My name is Benedicta and I'm part of the communications team here. Our monthly webinars are based on our technical reports, which are available from our website sustainable-carbon.org. Please type any questions in the questions box as we go along and we'll answer them at the end of the webinar. The subject for today's webinar is energy from waste, presented by Greg Kelsall. Over to you, Greg.
Thanks, Benedicta. Yes, I'm Greg Kelsall, Principal Associate with the ICSC. I'm going to talk about energy from waste. It's based on a report which I've been writing. It's out for draft until the end of this week, so you have a few days to comment on it, and it's due to be released at the end of this month. So presentation outline for today, I'll say a little bit about the issue of energy from waste and talk about the hierarchy of waste management. Then look at global municipal waste on a global basis and look at how it can be used in energy from waste plants. Look at some energy from waste technologies. Then move on to opportunities to decarbonize energy from waste. We can also think about using municipal solid waste co-utilized with solid fuels such as coal, so I'll take a quick look at that. There's also the opportunity for materials recovery from energy from waste plant. Have a look at the required support for energy from waste, and then wrap up with some key conclusions. So firstly, look at the growing issue of municipal solid waste. So there are a number of wastes, so industrial waste, agricultural waste, but it's municipal waste, i.e. the waste that we produce in our households, that some industries produce, that is the most ubiquitous source of waste. And it's a growing issue. There's over 2.1 gigatons of MSW generated in 2020 alone, and this is forecast to grow to perhaps as high as 3.8 gigatons by 2050. And this is driven by things like population growth, by the increasing move to urbanization, particularly in Africa and Asia, and by a general growth in living standards in the developing world. I mentioned the hierarchy of waste. So this is a conceptual framework that has been derived to help think about how we can deal with that growing waste issue. And it prioritizes waste in terms of how it should be treated. So firstly, we could think about preventing waste. So trying to have no packaging. Think about reducing the amount of waste, so designing our packaging and materials in such a way that we minimize the amount of waste. We could then think about reusing and recycling waste. Next in the hierarchy is recovery. So this is where energy from waste has a role to play. And then finally, the least desirable is to dispose of waste in landfill. So energy from waste is entirely complementary to this. It reduces the proportion of residual waste that would otherwise be sent to landfill and would therefore generate things like methane emissions. It represents the most sustainable solution to treat the non-recyclable component of waste. It contributes to the circular economy. So if we think about trying to maximize recycling, there'll always be a residual amount of waste that needs to be dealt with, and it helps to deal with end-of-life materials, and it produces a reliable and local energy from that waste, and it can also play an important role in hygiene. So as we'll see later, some waste is just disposed of and allowed to rot or burnt in open fires, and these can lead to local hygiene issues. So moving on to municipal solid waste as a global resource and how it might be used in energy from waste plants. This graph here shows the projected movement in terms of municipal solid waste production, starting from 2.1 gigatons per year in 2020 and moving through to 3.8 gigatons in 2050. And this is in the absence of any measures to control that waste, so it's the business as usual case. Around 38% or 800 megatons of MSW generated globally is what's called uncontrolled waste. So it's either dumped or it's burnt in open fires. And to some extent, this reflects the access to waste collection services, particularly in developing countries. So in sub-Saharan Africa and parts of Southeast Asia, 80 to 85% of all waste is in this uncontrolled category. If we then think about the controlled end users of waste, so either landfilling, reduction and recycling, or energy from waste, this constitutes the remainder. And energy from waste currently deals with about 275 megatons, or about 13% of that waste. That could increase through to 470 megatons of MSW by 2050. Even if we think about waste reduction measures, so not the business as usual case, but some of the other potential routes that we might follow, energy from waste is still expected to deal with about 450 to 470 megatons. Again, around 20 to 13% of MSW by 2050. The uncontrolled waste will still be significant in 2050, 1.7 gigatons, and so clearly there's further potential for MSW to play an even larger role than the 450 megatons that I've mentioned. Looking at the composition of the MSW, it varies on a global basis, and this is largely dependent on the GDP of that region and on consumption patterns. So if we think about the Western world, where food is produced and then transported over long distances to where it's used, there's a higher proportion of packaging, so things like paper and cardboard. Whereas in some of the developing regions, it's more food and green waste that contributes a larger proportion of the overall MSW. So the plot here shows that food and green waste is the largest element of waste, followed by paper and cardboard and some other components. The calorific value of the waste is around 10 megajoules per kilogram, and it has something like 60 to 65% biogenic content, i.e. typically food and green waste and paper and cardboard. In the UK, that value is something like 54%, and that's typical of some of the more developed regions. In the longer term, we could think about the biogenic content perhaps reducing to around 50% as more recycling and reduction measures are introduced. So I think that's a good long-term view of what the biogenic content of waste would be. Calorific value of 10 megajoules per kilogram. Energy from waste plant typically needs 6 to 7 megajoules per kilogram. In terms of energy and electricity generation, particularly from that waste, the total energy production from biomass generally is around 685 terawatt hours in 2020. The proportion of that produced from MSW is 77 terawatt hours, So it's around 13% of the total energy produced by biomass, and it's growing roughly at 4% per year from 2020 through to 2000 through to 2020. Europe typically leads in the production of energy from MSW, with around 64% of that 77 terawatt hours produced in Europe, whereas Asia tends to be more dominant in industrial waste and production from energy from waste. If we think about the total global electricity demand of 28,400 terawatt hours, then this energy from waste is less than 1% of total electricity production. In UK, that figure is more like 3%. So clearly there's some regional variation in terms of electricity production. But whilst energy from waste will be a reliable source of energy using a indigenous source of fuel, so something that can operate flexibly around variable energy demand, clearly it won't be a major contributor to the overall global electricity demand. In terms of the number of energy from waste plants, there's around 1,800 to 2,500 energy from waste plants globally. The range of number reflects the inconsistency of data in the waste area, and that's a kind of a general thing that I've found. Those plants are typically found in the Asia Pacific region, around 60%, a third of them in Europe, and a small number in North America. And I'll show you here a plot of how those, for Europe, of how that's distributed among the European nations. And the numbers typically reflect the GDP and population size of those individual countries. If we look at the average plant size, globally it's around 40 megawatts average plant size, with more than 60% of energy from waste plants being 10 megawatts or less. So this reflects the localized solutions that MSW can offer, particularly in cities and urban locations. But having said that, as I'll come on to later, I think as we start to think about net zero emissions and transition plans, then it's some of the larger energy from waste plants that will probably start to dominate. So having looked at the kind of background to energy from waste, I now want to look at some of the energy from waste technologies that could be used to deal with the waste. So the typical technologies are incineration, gasification and pyrolysis, as well as anaerobic digestion. And these are all available at high commercial readiness levels, so typically in the 7 to 9 region. Anaerobic digestion is a low temperature process, and therefore it's more suitable to biodegradable wastes, which can be dealt with through anaerobic processes. Whereas for the treatment of municipal solid waste, it's more the high temperature thermal treatment processes which are best suited. So incineration, gasification and pyrolysis. Incineration typically operates at 850 degrees C and produces heat and electricity through steam turbines. Gasification produces a syngas, which can be used as a chemical precursor, but also in energy plants. And similarly, pyrolysis, again, can be a precursor for chemical plants, as well as a source of power production. The first of these then is incineration, and this is by far the most common technology, representing more than 80% of energy from waste plant. It's a reliable process and can control emissions of pollutants and dioxins. And the plot here shows a typical waste to energy plant where you would feed waste into a waste pit. This is then transferred into the combustion chamber of the incineration plant, which is typically a travelling grate, although it can also be a rotary kiln or fluidized bed. Heat is then taken out from the process via a steam turbine, typically at 400 degrees C and 4 megapascals pressure. And this can deliver generation efficiencies of around 20%. Within the boiler, the temperature is typically in excess of 850 degrees C with a 2 seconds residence time for control of dioxins, and by operating at low oxygen levels, it also helps to control NOx emissions. And we then have an air pollution control system on the back of the plant, usually based on a bag filter based system operating at 200 degrees C and below. Looking at that air pollution control system, so this is a key part of energy from waste and its public acceptance. The cleanup process is typically based on a bag filter system. So this would remove dust by injecting alkali substances, and by injecting activated carbon. We can also control acidic pollutions, so hydrogen chloride and SOx, and the activated carbon can capture mercury and dioxins. And these are all removed with the bag filter and captured as part of the residual fly ash. And that fly ash is typically treated as an industrial toxic waste and landfilled in the correct manner. In terms of NOx emissions, we have to think about controlling these within the incineration process itself. So the combustion process, by controlling the oxygen level, this can help reduce NOx emissions to low levels to start with. And then we can have a selective catalytic reduction or a selective non-catalytic reduction system to effectively remove the majority of the NOx. So the non-catalytic system injects ammonia at the high temperature part of the process, and the catalytic reduction system, using things like titanium oxide or vanadium pentoxide, at the lower temperature part of the process, so after the bag filtration removal system. And by a combination of these control measures, we can effectively eliminate particulates, NOx, SOx, dioxins and mercury from the energy from waste plant. Some alternative technologies are gasification and pyrolysis. So gasification typically operates at temperatures of 1800 degrees C, pressures of 0.6 to 2.6 megapascals. By operating with a low oxygen level, can produce a syngas of carbon monoxide, hydrogen and methane, and with further processing can produce pure hydrogen. And as I mentioned earlier, this could be used for power generation in an integrated gasification combined cycle system, and this offers the potential for higher efficiencies than the 20% that I mentioned for incineration, or it could be used as a precursor in chemicals and heavy industries. It does, however, typically require a more homogeneous fuel than the MSW, which can be treated in an incineration plant. So this is an RDF type fuel or an SRF type fuel. The exception is plasma gasification, which can handle raw MSW. This typically operates at 10,000 degrees C, but it does need a higher energy consumption to do that. So the electricity demand is typically 1,200 to 2,500 megajoules of electricity per ton of waste treated. But there are commercial examples of plasma gasification, and I show here one which is being offered currently. Pyrolysis is a further treatment process, and this operates in a way kind of similar to gasification in that it's a low oxygen process, although operating at a lower temperature. And this time we can produce a pyrolysis oil, a pyrolysis gas, or a solid coke. And again, it can be used for power generation, or it can be used for chemicals. But again, it's best suited to homogeneous fuels, and so typically needs SRF or an RDF fuel source. So having looked at the technologies, I now want to look at some of the opportunities to decarbonize energy from waste. So thinking about the fuel that energy from waste uses, as I showed earlier, it typically has a biogenic content of around 65% on a global basis. So this means that the biogenic component of energy from waste, when burnt, is effectively net zero. The fossil fuel component, so things like plastics, does have a positive emission. But if we then add carbon capture and storage to the energy from waste plant, so can capture 95% or maybe more of the CO2, then the plant or the biogenic component of the plant is then a net negative emission, and the fossil fuel component then becomes net zero. So overall, the energy from waste plant is a net negative or a greenhouse gas removal technology. There's also the advantage that if we divert waste away from landfill, it means that the waste wouldn't then produce methane in the landfill, and methane has a much higher greenhouse warming potential, so something like 28 times the warming potential of CO2. So it's positive in terms of reducing methane emissions from landfill, but by installing carbon capture and storage, we can also be a net negative power plant producer. So looking at that greenhouse reduction potential, the pathways to achieve zero emissions by 2050 all require greenhouse reduction. So the IEA net zero emissions pathway needs something like 1.9 gigatons of CO2 per year of negative emissions from biomass carbon capture and storage and from direct air carbon capture and storage by 2050. Projections from the ICSC has even higher levels of BECCS and DACs being needed, something like 3.5 to 16 gigatons of CO2 per year by 2050. The greenhouse gas removal potential of energy from waste. So if we retrofitted carbon capture and storage to all of the energy from waste plant, this could deliver something like 220 megatons of CO2 per year by 2050. And that would represent 12% of the net zero emissions pathway requirement of GGR. A further advantage of energy from waste is that it's available in the relatively near term. So the fleet of energy from waste plant is already installed. Carbon capture and storage technology is commercially ready and available to go. So the the kind of critical path would then be dependent on the availability of CO2 transport and storage. So I highlight that in the plot on the right-hand side here, which is focused on the UK, but it shows that by 2050, energy from waste could contribute 87% of the greenhouse gas reduction required by the UK. But earlier on, so in 2030, 2035, it could contribute 27%, and in 2030, it could contribute 40%. So it's a readily available technology, and it can get us on the pathway to net zero more quickly than some of the other greenhouse reduction technologies. The pipeline of energy from waste plant with carbon capture and storage projects is already building, and there's something like 21 energy from waste plant in the CCS pipeline, as shown by the Global Carbon Capture and Storage Institute. Now that's a relatively small proportion of the total CCS pipeline. So we think about there being 450 or so plants altogether. It's around 3% of the total number of plants, but it's growing. So that represents 3% of the total plant. It represents about 1% of the total CO2 storage potential at just over 5 megatons of CO2 per year. So I think, as this chart shows, it's really Europe that's dominating in terms of that pipeline. So 90% of the proposed CCS projects are based in Europe, and a large number of those, more than 50%, are actually based in Scandinavian countries. I just want to highlight one of those projects as an example of what's happening. So this is the Hafslund energy from waste plant based in Klemetsrud in Norway. It's been producing power since 1985 and is the largest single point source of CO2 in Oslo. It treats 350 kilotons of waste per year, and once CCS is installed, it's planned to capture 350 kilotons of CO2 per year. There's actually been a pilot plant, a pilot carbon capture and storage plant operating at the site since 2015 as part of an earlier feasibility study carried out by ACA. They then thought about moving to a Shell Kelsall based system, but more recently through the latest feed study that they've done and the latest cost reduction activities that they've done, now focusing on an SLB Capturi in combination with an ACA based modularized Just Catch amine based post capture system. So the EPC contract for that has just been placed with SLB Capturi and ACA, and the plan is to start actually building the carbon capture and storage system early this year, with the plan that it will be fully commercially operational by the third quarter of 2029. The EPC contract will provide not only the capture system, but the intermediate CO2 storage and the ship loading that will be needed to take the CO2 for permanent storage in the Northern Light project, for permanent storage in the Norwegian sector of the North Sea. Hubs and clusters. So I mentioned earlier that it's likely that carbon capture and storage will first be installed on some of the larger energy from waste plant. So I show here an example in the UK, which is the HyNet cluster project. So this will take CO2 and store it 1 kilometre below the seabed in the Irish North Sea. There are 2 projects within this cluster which are energy from waste related. So that's the I forget the names of them at the moment actually, but there are 2. It's a Viridor plant and Protos Energy, which together will capture more than 1.2 megatons of CO2 for permanent storage in the Irish Sea. So I think it's these larger energy from waste plants that will count for early deployment, because they can take advantage of the CO2 storage and CO2 pipelines that will be provided by these large industrial clusters. Although longer term, there will be the potential for more dispersed energy from waste assets, potentially using rail or truck transfer. And then even longer term, there's potential for smaller energy from waste facilities, which aren't necessarily contained within these industrial clusters, but they could maybe use their CO2 in local greenhouse and industrial applications as part of circular economy solutions. Looking at the cost of energy from waste with carbon capture and storage. So based on studies in Europe, the overall cost of CCS and thermal waste treatment is estimated to be in the region of maybe 75 through to 130 euros per tonne of CO2. We expect that cost to fall through things like solvent innovation, through process integration, and through intensification, and just generally through the kind of learning by doing that energy from waste plant will deliver. The majority of the cost relates to the capture system, so that accounts for maybe 50 to 60 euros per tonne of CO2. The transport element clearly depends on the length of the pipeline needed, but that will typically cost 1 to 2 euros per tonne of CO2 per kilometre of pipeline. And then the remainder of the cost relates to the compression and the actual storage costs. Moving on now to co-utilisation. So if we think that coal will remain the dominant source of energy for much of Asia, then MSW, or more significantly the biogenic proportion of MSW, could be used to co-fire with coal and therefore to reduce its CO2 emissions and make these plant zero, or if the co-fire ratio was very high, maybe a net negative emission when combined with carbon capture and storage. Some studies in China have, however, found that adding MSW to existing pulverized coal plant can increase the potential for NOx emissions, for HCl emissions, and fouling and slagging within the existing pulverized fuel plant. So this may limit the amount of co-firing if it's solid RDF and SRF co-fire with the coal to around 10%. We could, however, convert the MSW into a waste to fuel, so convert it to a syngas or a hydrogen or ammonia, rather than co-firing solid RDF, SRF mixed with coal. And by doing that, we could get around this issue of slagging and fouling, and could therefore go to higher co-fire ratios, and therefore deliver net zero emissions in coal-fired plants. In kind of western regions where coal assets are being decommissioned, There's also the potential to repurpose some of those coal assets by converting them to energy from waste plant. And I show here an example of what was the Ferrybridge coal-fired power plant in the UK, which is now an energy from waste plant. So it's repurposed and reused some of the infrastructure of that former coal-fired power plant. Materials recovery is the next area I want to look at. So energy from waste plants can produce materials from the residual fly ash and bottom ash within the energy from waste system. This can lead to additional recycling of metals and minerals, which otherwise would have escaped the recycling available earlier on in the hierarchy of management. If we can recapture metals, this can reduce the dependence of countries on primary materials such as steel and aluminium. It can contribute to the CO2 reduction of those sectors. So thinking about aluminium, for example, recycled aluminium uses 5% of the energy of producing primary aluminium. So clearly it can be a major contributor to CO2 reductions of that sector. And it also produces an additional revenue stream for the energy from waste facility, so helping to contribute to the economics of such a process. Metals recovery then. So bottom ash typically accounts for 20 to 25% of the weight input of an energy from waste plant. The bottom ash itself is 80 to 85% weight of minerals, and of that 10 to 12% weight is ferrous metals, so steel and iron. So these can be separated by conventional magnetic separation technologies and can recover 85 to 95% of those residual ferrous metals. It also contains around 2 to 5% of non-ferrous metals. So this includes things like aluminium and copper, and they can be captured by eddy current separation processes. Now currently around a third of these non-ferrous metals are recaptured in European energy from waste plants. So clearly there's significant scope to capture more of these non-ferrous metals. Now that's partly due to some of the difficulties of capturing things like aluminium, due to the chemical complexity of how the aluminium is bound within the ash. But nevertheless, clearly that there is scope for significant further capture. Mineral recovery is a further opportunity. So once the metals have been recovered, allowing the ash to stand for 6 to 20 weeks, the ash can then be stabilized and used as a source of minerals. So these minerals could be used as secondary aggregates for road construction and in building projects. Now, in countries like Denmark, legislation has already been introduced to allow bottom ash to be used in these construction projects, and there 99% of the bottom ash is now recovered and used in this way. So if that was rolled out to other countries, now there's good potential to utilize the minerals as well as metals in these kind of applications. So now I want to move on to the final area that I'll look at, which is the support required to make these energy from waste plants happen. At an international level, the things like the Kyoto Protocol and Paris agreements have set countries on a path to net zero emissions and shown how energy from waste can contribute to that. National policies are also being introduced. So in the EU, we have the Waste Framework Directives and the Net Zero Industry Act, which came into force in June of last year. And the Net Zero Industry Act is looking to provide 50 megatons of CO2 capture infrastructure in Europe by 2030. In the US, there's the Renewable Portfolio Standard, and other countries also have their own policies looking to provide the framework for energy from waste plants to materialize. There are also financial incentives through instruments such as feed-in tariffs, through landfill taxes, which typically increase in value per year, and through guaranteed power offtake agreements for energy from waste plants. Carbon pricing is another mechanism which will promote carbon capture and storage systems. So in Europe, there's the emissions trading scheme, for example, which now recognises energy from waste within its cap and trade system. The carbon price in Europe reached a high of 100 euros per tonne back in 2022, and it's forecast to increase perhaps as high as 200 euros per tonne by 2035. And at such a level, things like energy from waste with their net negative CO2 emissions start to become really attractive. And as legislation is also introduced to recognise secondary products from waste so that these can compete with primary and virgin sources of metals, for example, this all contributes to the required support from energy from waste. Public acceptance will be another key area. So we consider public attitudes as being vital to the transition to net zero emissions. And I highlight here a couple of studies which have been carried out by the IEA in Copenhagen, and a further one carried out in Italy. And these show the kind of importance and provide examples of how energy from waste can be integrated into urban areas. And the plot here shows a nice example of how an energy from waste plant can be shared in an urban area by providing things like key slopes, dry ski slopes, and shared public amenity facilities combined with that energy from waste plant. It shows how communications with locals is crucial to integrating energy from waste plant in local communities. Using the best available technology leads to enhanced environmental performance, which is also important. It also shows the need for communication to push forward the net benefits of energy from waste plant, and that the transition cannot be complete without building public trust. Public trust between the energy from waste providers, probably more crucially government and the suppliers of policies and how these are driven forwards. So finally, I just want to wrap up with a few key messages. So I think I've highlighted the growing issue of waste, how waste is currently the level of 2.1 gigatons per year, and in the absence of measures, it's going to increase perhaps to 3.4 to 3.8 gigatons per year by 2050. The energy from waste can play a key role in the overall waste management hierarchy to deal with this waste. It can process around 450 megatons of non-recyclable MSW components, so around 13% of the total MSW, and can reduce the amount of waste that would otherwise be sent to landfill. At the same time, it can produce 1% of the global electricity energy demand. Not a significant proportion, but an important contribution nonetheless, and one that is reliable and uses indigenous energy source of fuel. It can recover materials that were not recovered earlier on in the energy from waste hierarchy. So it can recover iron, aluminium and other metals, and can use those to support the circular economy. But perhaps the most crucial contribution is that energy from waste could contribute up to 12% of the greenhouse gas reduction that the IEA thinks will be needed by 2050. Okay, so thank you for listening. As I said earlier, the report is out for comment currently, and we plan to issue the report in full and for it to be available on our website by the end of this month. Okay, and I provide here my email, so if there are any further questions or clarifications you have, please feel free to contact me directly. Right, so I'll just open up the questions pane and see if anyone's asked me any questions. So one question is that I've heard about the cluster sequencing process in the UK. Could you say anything more about that? So yes, cluster sequencing. So this recognises the importance of hubs and clusters in the UK, sees carbon capture and storage as a key part of how the UK will decarbonise its energy systems through to 2050, and so focuses on industrial carbon capture and how that will be rolled out. So that the cluster sequencing process has set aside £21 billion of funding for the first wave, so for the cluster 1 projects. So I showed the HyNet cluster, and that's one of the first 2 clusters, together with the East Coast cluster, that will deliver that first wave of decarbonisation. The HyNet project has 5 such emitter projects, and 2 of those are energy from waste. And the East Coast cluster has 3 projects. We then plan to roll out those roll that out further, partly driven by the increase in the carbon price, which should then start to make such projects more economically viable as we go forwards. Okay, I don't see any further questions, but like I say, please feel free to contact me on my email address if anything further occurs to you. Okay, so that concludes the webinar for today. Thanks everyone for listening.
Thank you so much, Greg. And all that's left for me to say is the slides from this webinar will be available to download from the webinar page of our website shortly. Thank you all for joining us today, and goodbye.